Okay, so on section 5.2, page 550 or 454, and this is called proving trig identities, and this is you've got to do it to learn it kind of section. So I'm just going to jump right in, but I'm not going to do example 1. If you want to see that example 1, does it involve any trig? Would that be more comfortable? We didn't do a trig one? So you can relax on that. Okay, so example 1 is an algebraic one, and it says prove that this identity is true. X squared minus 1 over x minus 1 equals, or no, minus x squared minus 1 over x plus 1. We're trying to prove that that equals 2. When you encounter when you're actually trying to prove an identity, there are a couple of rules you have to adhere to, and if you do not adhere to them, you will run into all kinds of trouble and have to start over. One of them is, when you are trying to prove an identity, you may not cross this barrier ever. You work on one side or you work on the other. The objective is to get one side by algebraic manipulation and all sorts of tricks and things that you do to try to whittle that thing down until it equals the other side. But you do not take things from here over to here by addition or subtraction or dividing it, because the objective is not to solve. We are not trying to find the value of x that makes this true. Get it out of your head. What we're trying to do is to show that this side actually has a value of 2 no matter what x is. That's what we're trying to do. And so you cannot, when you're doing identities, do not cross that equal sign. And you generally start, as a general rule, this is not cast in stone. This right here, you generally start on the more complex side. Doesn't mean you can't eventually move to the other side and work on it a little bit. The objective is to do algebraic tricks, manipulations, apply all the algebra you know to continue to let this thing evolve into something. And if you get stuck here and you still haven't got it to equal that, then if you want, you can go over here and start working on that until this side looks like this side. And when you get this side to look exactly like this side so that there's an equal sign, then you circle both of them and stop. Then you've done your proof. Then it's done. There's nothing to work on this side, so it's all going to happen over here. I mean, 2 is 2. So what we do is we begin to start with some algebraic stuff like this right here. That's a difference of 2 squares, so I'm going to factor it. That's a factorable thing. Now, I say you can't cross this line, but if you need more room to work, if this gets really fat, then you can extend your line out. Just don't take things over there. Okay? That's all I'm saying. Okay. So, oh, look at that. Those cancel. Oh, we got that to cancel. Good. So what I'm left with is x plus 1 minus all of x minus 1, because that minus sign applies to everything that's left over here. And I have x plus 1 minus x plus 1, and that is 2.
So if it didn't cancel out, would you find a common denominator?
Yes. So that's an algebraic one. And the objective is one side to look like the other by algebraic manipulation. And the appropriate application of identities. That's what's going to show up next. The identities that you have, the 11 that you have to work with. You can replace certain statements with those identities that you know are equal until they look alike. And that's the main goal of trig. This didn't have only trig, but the idea is here. Okay, so I'm going to erase this one, go on to the next example, which is trig, I think. And if you have not done anything on section 5.1, you haven't worked with the identities, so they're not really in your head yet, you're going to have a rather difficult time understanding what I'm doing. I don't know what to tell you. Get it done on time. Example 2 says, prove the identity. Tangent x plus cotangent equals secant cosecant. Tangent x plus cotangent x equals, what is it? Secant cosecant. Did I not get that right? Tangent plus cotangent equals secant cosecant. Yeah. Did I write it right? We good? Yeah. Okay. Now, please don't look at the solution. I want to try to help you think about what you need to do. It seems very strange to me anyway, and rather impossible looking right at the outset, that I can turn a sum into a product. First of all, that was weird to me. right? But proceed with faith. Which side would you like to work on? Katie wants to work on the right side. Or would you rather work on the left? I'm telling you, if you choose to work on the more complex side, because that's what I've told you usually happens, then you would work on the left. Addition is more complex to deal with because you have to find common denominators and stuff like that. Addition is more complex to work with than multiplication. It doesn't matter. Start on something. I'm going to start on the left. Katie wants to start on the right. It's my problem. I'm doing it on the left. It's not necessarily correct. I may back clear off, erase everything, and then start on the right again if I run into a wall. And that's what you got to do on this. You just got to start. Just do something. Start to manipulate things, start to rewrite things. And if you have no clue where to start at all, start by by converting everything to sine and cosine. If you have no other way to begin, you have no idea, no clue what to do. And that's what I'm going to do. I'm going to write sine x over cosine x. And the thing is, the reason why people are reluctant to do this is because it makes what was simple much more ugly and complex. But it's like I said, it's darkest before the dawn, right? You got to make a mess and then clean it up. So this is cosine over sine. And I now have a fraction that needs a common denominator, as Katie was noting in the last one. If they didn't cancel out, you'd have to find one. So I need to multiply this one by sine and this one by cosine. And when I do, they will all be over cosine sine. Y'all following that method of handling fractions or not? Because I need to explain it if not. Andrew, you're not nodding. Are you? You do? So the next thing I write over here is going to have a cosine sign in it, like that. And what's going to be up here is sine squared plus cosine squared.
Oh.
You following that? The dawn is dawning. I mean, it's getting lighter now. This was the darkness. Now it's lightening up. You start to see it. This is 1 over cosine sine. And this is the only case. This is the only case where you can split up a numerator. 1 is 1 times 1, right? So we can write that 1 as 1 over cosine times 1, because I'm still going to get a 1 up here, over sine. You can't do that with any other number. You know, we can do it with 2 if you put a 2 here and a 1 here. You can't just split it up arbitrarily. 1 is the only one you can do this with. And 1 over cosine is secant. And 1 over sine is cosecant. Voila. Did you catch all that?
Yeah.
Pretty crazy. I know. All right, next one. That was the first one. It's always easier. Yeah, boy. All right, example 3 is kind of, I'm not actually going to do it with you unless, well, you might want to try it. Example 3 is kind of bizarre because, well, here's what they do. It says, match the function. They give you a function, not an identity to prove. I'm on page 456, and you need to look at what they're offering you, because they'll do this to you on the exercises. They give you this function, and it's ugly. It's 1 over secant x minus 1 plus 1 over secant x plus 1. And it says, of these two, and it's not even Roman numerals, but they're I and I, 1 and 2. It says, of the following, decide which one of these two is equal to that function by graphing them, and then confirm the match with a proof. So, what they have there on the left of example 3, those 3 graphs they have there, the top one is the function, 1 over secant x minus 1 plus 1 over secant x plus 1. That's that function. Looks like a couple of wine glasses next to each other, right? The next graph, which is 2 cotangent and cosecant, looks exactly like it. The next graph, which is 1 over secant, which really cosine, is the bottom graph. Obviously, the number 1 offering matches the function itself. That's what they're saying. You got to graph all 3, and the 2 that match, you have to prove that they are the same, because graphically they are, so we have to prove it algebraically. You see what I'm saying? That's a practice. They're forcing you to practice graphing these 3 trig functions that are hard to do. I assume you can, and if you can't, you're going to have to get some help with that. But I am going to go after the identity because I'm running out of time. So I want to prove that the f of x that they gave me is equal to 2 cotangent cosecant. Yeah? Okay. So I have 1 over secant is the first one
X minus 1.
minus 1 and then plus?
Yeah.
1 over its conjugate?
Yeah.
And I want to prove that it's equal to 2 what?
Cotangent and then cosecant.
Again, I've got a sum of something I'm going to prove it's going to be equal to a product. But you saw how that fell out. We had the sum, but it turned into a single thing. There's where your product came from. So it works out. Have some faith. All right, so do you want to work on the left or the right?
Right.
You're going, the right's nicer. I want to work on the right. No. Bite the bullet, work on the left. Common denominator, right? I mean, correct? Secant x. Whoa. That's my common denominator. This one is just a 1, and it needs multiplied by the piece that this is missing, which is that. Did I lose you on that? You do most of that in your head because you're going to be doing that a lot. And so if you can take some shortcuts, it's better. Are you okay with that? This then turns into 2 secant. Yeah? Yeah. Over secant squared minus 1. The reason I waited to multiply these out is because I wanted to see how this turned out. Because if in factored form, it's a lot easier for me to see if the result of putting these together is cancelable. It wasn't. So I went then and multiplied it out. You see what I'm saying? Leave it in factored form until you're sure nothing will cancel once you clean up the numerator. And it doesn't. So I multiplied them together because when you have a binomial times its conjugate in trig, you generally always produce an identity. Do you see that Pythagorean identity? Is it there? Was that an identity?
Yeah.
What is it? Is it tangent squared? Yeah, there you go. Look it up. Get it memorized. Is that really an identity? Tangent? Tangent squared. So it's 2 secant over tangent squared. Now what? Do you want to continue working on that? I mean, we could turn this into sine. We could turn this into 2 over cosine, and this into sine squared over cosine squared, and then invert multiply. I mean, there's more we can do here. Would you like to? We can. You want to keep working on this side? All I'm saying is you have the option to work on this side as well. We don't have to. I'm actually, if it were me doing this, I would continue working on this until I ran into a wall. I'm not there yet. I haven't hit a wall yet.
Keep going.
Should I keep going? Okay. Now, please keep in mind that this is the only board space I have, and I am not crossing the equal sign. I'm just coming up here to continue working on the left side, so don't panic. It's just I'm out of space, and I've got to stay on this board. Are you with me? Okay, so I'm coming up here, trying to shoot for this, but I'm not crossing that, so don't panic. Okay, all right. So I have 2 over cosine. Does everybody understand that?
Yeah.
And this down here is sine squared over cosine squared, which is 2 over cosine times cosine squared over sine squared. One of these is gone.
Wait, go back. Why is the 2 still up in the numerator?
Because that's 2 times, I'm sorry, because that's 2 times 1 over sine, 1 over cosine.
Oh, gotcha, yeah.
Okay, is everybody clear on that? Where the 2 ended up in the numerator?
Okay.
Yeah.
You weren't the only one with the question, apparently. Thank you for asking. Danny doesn't want to talk.
Sorry.
Okay. It's all right, but now he's going, yeah, oh, I see it now. Yeah, was everybody okay with that?
Yeah.
Okay, so we flip it over, we lose the cosine. Is everybody okay with that?
Yes.
So now what I have is, and this is really tricky, what I have now is 2 cosine x over sine x times 1 over sine x. Splitting it out. 2 times cosine over one of those sines, because I'm keeping in mind what I'm shooting for. I've got that tucked away in my mind. I know what I'm shooting for, and it's not squared things. So I'm going to split that sine so that it's sine times sine, and I'm going to put the cosine over one of them and 1 over the remaining one because that's all that's left in the numerator. And what I end up with is 2 cotangent. This is 2 cotangent. This is cosecant.
I have a question.
Yes.
Why does the 2 go to the cosine? Like, how did you get from
They could go with the sine. It's fine.
last 2 steps?
Or last two steps.
Yeah.
You understand how I got to here by flipping that up
Yeah,
and canceling? It's getting to here?
Yeah.
Okay, what's left is 2 cosine over sine squared. So I'm gonna take the 2 cosine and put it over one of the sines, and I'm gonna take what remains. I've already used up the entire 2 cosine to put it over one of those sines, and there's only a 1 left to put over the other one. What I'm doing is keeping this in mind all the time, what I'm shooting for. And I remember that cotangent is sine over cosine, or cosine over sine, not cosine over sine squared. It's cosine over sine. Oh, and that's the other sine. Oh, I see it now. You see what I'm saying? Now, we could have worked on this side here. We could have said, that is 2. Let me just show you real quick. I'll put it in red. If we got to somewhere down here, we said, okay, I don't know where to go next. I really don't feel like I want to work on this side anymore. That's fine. You could have rewritten this as, starting on this side, you could have gone 2 cosine x over sine x. And the 2 doesn't have to go with this one. It could go with this one. Times 1 over sine. And I'm not sure how much farther you could go with that, but you could get to this point right here and go, oh, they're the same. Okay, you with me?
Yeah.
So we could have worked on that side a little bit. I just stayed with this one and we eventually landed there. This is a harder thing to come up with, that this turns into this, turns into this, than this turns into this, which is sitting right there. Whatever you want to do. You run into a wall, try working on the other side for a while. Okay. Example 4. I'm just teaching you some tricks. Try to always keep the side you're not working on kind of sitting there in your mind, remembering your target. It helps steer the proof instead of just blindly turning things into other things. Sometimes that's your only option. Just keep moving on it until it gets closer. You go, oh, now I see it. The main thing here is to persevere. Don't give up. Don't say, I don't know what to do next. I'm just going to quit. Keep trying something. Oh, grab the book so I can write it. Okay. So it says, prove the identity. Gosh. Can't read that. Cosine t over 1 minus sine t. And the other one is 1 plus sine t over cosine. Boy. One looks like the reciprocal of the other, except for the conjugate sign is different. And that makes all the world of difference. This is a trick that it may not occur to you to do at this point, but you might want to use. Do you remember I told you that when you can multiply a binomial by its conjugate, it almost always produces an identity, a Pythagorean identity? Well, I don't have a binomial times its conjugate, so I will create the situation. Multiply this by 1. A 1 that's named 1 plus sine over 1 plus sine. That is 1. And I'm multiplying this fraction by 1, which means I'm not changing its value, but it will change what it looks like by doing that. You following? Okay, so what I have is cosine t times 1 plus sine t. I'm not willing to FOIL that out yet. I'll leave it in factored form. On the bottom, I have 1 minus sine squared. Because that's why I multiplied by the conjugate to create the situation, and that's cosine. One of the most, once you guys get started on this, one of the hardest things that's going to be for you to do is your mind is going to look at that and go, I can see what's going to happen, is to slow down long enough to write it properly. Because I can see what's going to happen too. I can go right to the bottom, but you got to show me that you know how to get there. So slow down and write down what you should do. I mean, I can see that one of these cosines is going to cancel with one of these cosines, but I want to see it. So you have to write it. It's going to take a lot of paper. It's going to take a lot of graphite, and it's going to take a lot of patience, because after you've done this for a while, you can see what's going to happen. You've got to show me. So one of these goes, and I have 1 plus sine over cosine. Oh, awesome. Done. See it? Use conjugates when you can. If you only have a binomial that you wish you had the square of it. Use conjugates, but make sure you multiply the numerator by as well. Next one. Cotangent, I'm gonna put an X instead of U because I'm just used to writing that and I'll screw it up, so I'm just gonna write, and you can too. Just put any variable that you're comfortable with in there. Cotangent squared X over 1 plus cosecant X equals cotangent X. Oh, that's all in one. It's not a fraction. Tangent X. I don't know why I use small t's and everything else is capital, but it's weird. Secant X minus tangent X. Okay, so we come up with some other strategies on this. Now over here, we just used a conjugate. It looks like it might be useful here. Maybe it is. Is that where you want to start? You really think they're going to use the same strategy again, one example to the next?
No.
Okay, that's what I'm going with. Do you want to work on the left or the right? They both seem equally complex in different ways.
Do the,
Let's do it right.
show the right.
Okay, and what do you want to do to the right? Do you want to distribute?
Change everything.
What's that?
Change everything. Cosine.
I'd rather change everything to sine and cosine because then as I distribute, perhaps I will be able to see better things that will cancel. Okay, so I know that, and these tricks and ways of doing things, they just come to you and you use them again in subsequent ones, but you just got to practice it. There's no reason why you should know to do this. Just experience. Okay, so cosine over sine times 1 over cosine. See what's going to happen there? Nice. Yeah. Okay. Minus sine over cosine. Okay. As we distribute that, that's going to cancel the cosines in that one. I'll have 1 over sine. And I know that you know what that is. Leave it alone for this step. Multiplying this one, the cosines cancel and the sines cancel. Yeah. And so I end up with cosecant x minus 1. That doesn't look anything like that side. So now I got to start working on that one because I don't know what to do. I don't know what else to do with that. So what could we do to this side? You should see the light on Akira's face. She's going, I know exactly what's going to happen. Okay, because you're starting to see it. What do you want to do?
Well, the top cotangent squared x is just cosecant squared minus 1.
Is it?
Yeah.
Okay.
Would you try to get an identity on the bottom?
Nope. I would like to follow Akira's lead. Cotangent squared is cosecant squared minus 1. Is that right? Everybody, y'all recognize that?
Yeah.
This is one way to do it. You could work on this side. If this did not occur to you, what it did to Akira, if that did not occur to you to do that, then you can change everything to sine and cosine and it will work out for you too. Maybe with a couple extra steps, but it'll work. She saw the identity in the square, and I reminded her of this yesterday, but she's not remembering either that or she's just being very polite, not participating right now. But you have to remember that not only are these identities, Amy, they're differences of two squares too, which are factorable. That's what we're going to use here because one of the factors of this is this. And once you've canceled this with one of the factors of this, the remaining one will be that.
Oh, that's so I see.
The difference of two squares, so that if I factor it, and you have to show me once you see it, you have to show me it's cosecant x minus 1 and cosecant x plus 1, because it's still a difference of two squares, which you learned to factor in algebra 1, probably pre-algebra, over 1 plus cosecant. So don't forget, this plays two characters. It's not only an identity for cotangent squared, it's also a difference of two squares, which behaves algebraically the way you hope it will. What am I doing? 1 plus, oh, yes, see, get to talking. Sure. Gone, cosecant x minus 1. That came from working on both sides.
So sometimes you have to work both sides.
Sometimes you will. Sometimes you'll work on one side, you get it all cleaned up and whittled down to something very, very nice and clean and simple, and you look at that and you go, crap, that's not even like it. So now you got to start whacking that thing down until you can make it turn into that too. Okay. And let's say, for example, and this hardly ever happens, but let's say, for example, you got it whittled down to here and it turned into this. Even though you've gone to here, you can still circle this and this. Whenever something on this side looks like this one exactly, you can be done. Okay? And one more thing before I leave this. If this did not occur to you, most folks would not see this identity. I didn't. I'll be honest with you, I did not see it. I was ready to turn this into sine and cosine and this into sine and cosine, all the things I can, and then manipulate that. It would still come out to this. There's lots of ways to get to the bottom. It just may have taken a couple extra steps. This was brilliant. Okay. Okay. The last one is going to seem really strange to you. But you need to practice. I mean, most of the stuff that we've done today, while it seems really difficult and you've got to know those identities and everything, they're handled pretty much the same way. When you use this stuff in calculus, it's slightly counterintuitive. So I'm going to show you one calculus proof. Most of the ones you're going to be dealing with are like these ones that I'm erasing. Show you where you're headed with these kinds of things when you have to use them in calculus. Okay. At the top of page 49, it says, in most calculus problems where identities play a role, the object is to make a complicated expression simpler for the sake of computational ease. Occasionally, and this is the exception, occasionally it is actually necessary to make a simple expression more complicated. That's more like with calculus. For the sake of computational ease. Each of the following identities, just a sampling of many, represents a useful substitution in calculus, wherein the expression on the right is simpler to deal with, even though it does not look that way. We prove one of these identities in example 6 and leave the rest of the exercises for the future. Notice in all 6 of these, they all start out with some power on a single trig function. Well, no, except for 6, there's a couple of them. And then they stretch it out. They make it more complex on purpose. And the reason why is because when you get into calculus, you will be wanting to integrate. You've seen that capital F sometimes? You're going to be wanting to integrate individual terms. And that's what we turn it into on the right. Like, for example, if I were going to do number 2, I would integrate the 1 plus tangent squared. No, I would. In number 2, I would integrate the 1/2. And then the 1/2 cosine 2x in 2 different integrals. And that makes it much, much easier than handling the sine squared. Because there is no antiderivative for sine squared. So you'll get there. All I'm saying is it can be useful to take something simple and make it more complex for the sake of integrating. So we're going to prove that they are exactly the same thing. A couple of things. We're just doing a proof. So it says in example 6, here's one, sine squared cosine to the 5th. We want to prove that that's actually equal to sine squared minus 2 sine to the 4th plus sine to the 6th times cosine. Believe it or not, this would be far easier to integrate, way easier to integrate than this. As a matter of fact, I don't know how I would tackle that one at all. Okay, so first thing to notice from left to right before you just dig in and then fight this battle. Notice that on the left we have 5 cosines, and the only cosines that show up here is this one. There's only 1, which means the other 4 cosines somehow magically turned into sines. That's the first thing to observe. So this is what I would do. You see if you can follow what I've written. I would do this. I would say sine squared of x is equal to 1 minus cosine squared of x times 1 minus cosine squared of x times cosine x. You see that at all? This cosine to the 5th, since there's only 1 cosine left in the entire answer over there, and I had 5 of them here and only 1 of them there, that means the other 4 have to be written in terms of sine because they're all sines now. That's all that's left over, sine and a single cosine. So I took this and thought of it as this. That's how I thought of it. And then I rewrote each of those. I'm sorry. I'm losing my mind. Now I wonder why you're looking at me funny.
Okay.
There we go.
Okay, get it.
That's what I meant. Sorry, I was thinking cosine. That's my fault. Entirely my fault. If I was doing this on paper, I would not have made that mistake. I want you to know that working on the board up here, being short and having short arms is like doing your homework like this. So it's really hard. So that's my only explanation. It's not an excuse. Anyway, that's what it should be. Now you okay?
Yeah.
Okay. All right. So what if I foiled these together now that I've written them in terms of sine? Just those two guys right there. I would get 1 minus 2 sine squared x plus sine to the 4th x if I foiled them out. Do you agree? See what's going to happen? It's very close. I've got a cosine on the end. I've got a cosine on the end here. I've got parentheses there. I've got parentheses there. I didn't have parentheses to start with. I've got parentheses now, but they're not quite the same. I've got to distribute that sine squared. And that's a very useful thing. That is not much trouble to integrate. That's horrible. There's no skill for that. You got to rewrite it in terms of identities before you can work on it. That's one example of changing something that's simple to something more complex to make it easier to work on. The main thing to get started on this one was we are going to work on the simpler side instead of the more complex in this case. And the thing to notice is we had 5 cosines here and only 1 here. And everything else was sine, means these other 4 somehow have to turn into sines. And they did quite nicely, only I screwed it up and that's why you couldn't see it. Sorry. Okay, so you have your assignment. I gave you the assignment page, right? If you want to, I don't know if I listed it on there, but number 45 is a bonus problem if you'd like to do it. If you want to try it, that'll be worth points on the next test. Anyway, there you go. You can have the video to view if you forget some of the strategies. See ya.
When you do the bonus and you get a point.